You are, yes, yes, you are audible. Oh, so you can share your screen.
Okay, okay.
Hmm.
So I think you have to change some setting. You have to
Okay,
make me
sorry, sorry.
co-host or something.
Let me fix it. Let me fix it. So now you can try.
Just a minute. Is it visible?
Yeah, your screen is not visible.
Okay.
So let me introduce you first formally. Ramakrishna Patra is a senior research fellow in SN Bosch National Center for Basic Science. His interest is in quantum information foundation, and today's title of his talk is Classical Analog of Quantum Superdense Coding and Communication Advantage of Single Quantum. So, stage is yours, Ramakrishna. You can start now.
Thank you. So first of all, I'd like to thanks the organizer for giving me this opportunity to present our work and have a nice interaction with everyone, so we can get some good feedback. So today I'm going to talk about one of our recent work. As the host says, that this is the title of the talk is Classical Analog of Quantum Superdense Coding and Communication Advantage of a Single Quantum. I will come to one by one why we have given this title and what is the meaning of these things. So nowadays information is very ubiquitous, means it is everywhere now and there, and our life is surrounded by sending information from one place to another place. If the information sending system is broken down, we will be in a big problem, we will be like in a big trouble. So our aim in a long run as a society is to improve our communication system, information system, and harness the power of this different system, so that we can use these things to utilize even for a better communication and information sending system. So for that purpose, we actually have to categorize different resources which are useful in this communication task. And for that, we have to look at different aspect of the communication task, and we will broadly characterize these different resources in different categories. So and we will use different Troy setup where these uh, systems which are actually we are using for the communication may be helpful. Like sometimes we can use some classical system for the communication. Now as we know, there are some quantum property, we can use some quantum system. And if there are some other theory, might nature quantum may not be the ultimate theory, there might be some system which is post quantum, though it is completely theoretical till now. Those kind of system we also may be able to use in future. So I'll not go into these philosophical details, I'll go into the categorization of the resources. So mainly in the communication scenario, we actually use two different kind of resources. So the first one is the common past resource, that is called the type 1 resources. So what does this mean? So common past means in their common past, Alice and Bob has made and they have prepared something. Like they can prepare some state and they can share that. So some example of this will be, you can see this light cone. So in the common past, actually they are meeting and they are preparing, and in the future they are actually sharing this state. So example of this will be, in case of classical case, you can think of this as shared randomness. That is a common shared coin that is shared between Alice and Bob. Or you can think in case of quantum it as entanglement, which they can prepare in the past, and then both the party has each particle, and now they are separated. But one thing you have to note, as the party are now spatially separated, these things has no communication utility. So it is zero communication. You cannot use entanglement for communication. It is no signaling. And what is the another kind of resource? That is a direct communication resource. So what do you mean by direct communication? So Alice is actually sending some physical system from his lab to Bob. So Bob is receiving this after some time. So you can think of, like, in case of classical system, this is like some green ball or blue ball. Like if a match, let's say, happening between India and Pakistan, if India won, I'll send a blue ball, and if Pakistan won, I'll send a red ball. So I'm actually sending a physical system, and looking at the color of the ball, you will get the information. So broadly, there are two kind of resources. We'll use that terminology very frequently. So now let's us try to get habituated with the setup where we'll try to compare this system. So actually there are these two systems. This is type 1 system, that is actually direct communication, and this type 2 system, that is actually assisted, this entanglement. So both these system will be shared between Alice and Bob, and in this scenario we'll actually try to understand how to use these resources, whether they will be useful in different kind of communication task. So in this scenario, there are actually many possible scenarios. Like in the Bell scenario, this well-known Bell experiment. There are actually one input on Alice's side, one input on Bob's side, and there is output on both sides, Alice and Bob. Like they will be given a variable X and Y, then they have to answer A and B. But we'll not be focused on this Bell kind of scenario. There are many other scenario like random access code, but we will be focusing only on this Hollebo-Frankel scenario. What is this scenario? In this scenario, Alice is actually receiving a variable X from the referee. And with the assistance of some limited direct communication and some pre-shared resource, this is a common pass resource, Bob has to give some output B. Now, depending on this input X and B, the referee will decide, okay, I'll give you some payoff. So this beta is actually denote different tasks. This is the payoff. Given this pair of X and beta, how much payoff they will get. So this is firstly represented by Frankel and Weiner in their CMP paper. And in this scenario, they have made some comment. I will come to that gradually. So in this scenario, they have actually made the comment that, let's say this type 2 resource that is pre-shared between Alice and Bob, let's say it is shared randomness. Then they are saying actually, whatever task you can do with a d-dimensional quantum system, that same amount of payoff I can achieve with a d-dimensional classical system. So actually they are making a very strong comment that there is no advantage in sending a quantum system on top of a classical system if you consider shared randomness as a free resource. So this is a very strong statement, and they have actually made this statement. But one thing that we must note, that they have actually considered shared randomness as a free resource. You have to give this opportunity. This amount of shared randomness is arbitrarily free. They can use as many copy of shared randomness as possible. Now, one of the possible argument could be that, okay, shared randomness has no communication utility. So in a communication task, we can consider shared randomness as a free resource. But this line of argument is not true in general. If you remember that entanglement, pre-shared entanglement between Alice and Bob, that is also a no signaling resource. It does not have any communication utility. But does that imply that entanglement is also a free resource? Actually, it does not imply. The answer is a negation. So one of the most famous paper in this our field is quantum superdense coding. What this says is that if Alice and Bob pre-shared a entangled state, let's say maximally entangled state, and let's say Alice send a qubit from his side to Bob, the communication utility of this qubit system will be double. Like with the qubit system, they can send only one qubit of information, but with the assistant of this entanglement, the communication utility of this is 2 qubit. So this assistance of entanglement actually doubling the capacity of this quantum system, this information capacity of this quantum system. So we should not consider entanglement as a free resource. So what is happening in this quantum superdense coding is that a common pass resource, that is the entanglement, that is which has no communication utility, that can enhance the power of a direct communication resource. So quantum plus entanglement is actually greater than quantum. So entanglement is enhancing the power of quantum system. That is the famous result of superdense coding. Now we are asking a question like, this is true in case of quantum, but what about in case of classical? So the analog of entanglement in case of classical scenario is this shared randomness, which does not have any communication utility. So now we are asking, if you use shared randomness as assistance and we allow classical communication, will it be better than only classical communication? Can it enhance the power of this classical communication? So this is the classical analog of this superdense coding. We are asking the question in the classical level. And we are actually answering this question by affirmatively. We are actually showing it there exists a task where the utility of this classical challenge can be enhanced with the help of classical shared randomness. So let's move forward and look into the task, then it will be very much clear. So this is kind of a task or game you can think of this. Let's consider this restaurant game. Let's say there is an owner who have many restaurants, like those are named A, B, C, N number of restaurants. And there is a player Bob who wants to actually visit this restaurant and have some dinner. But there is some problem. One of the restaurant is closed. And which restaurant is closed? That is only known to the owner. And it is closed randomly. Like someday hotel will be closed, someday the D restaurant will be closed. So it is randomly closed. Now the owner is helpful. He'll say that okay, I'll let Alice know that which restaurant is closed. Like in this scenario, the restaurant B is closed. So the owner will tell Alice that okay, now the restaurant B is closed. Now they have a restricted communication channel. Like they can communicate only one bit of classical communication. One C-bit communication is allowed. Now Bob has to visit this restaurant. Now, what are the rule of this game? The first rule is that Bob should never visit a closed restaurant because he wants to have dinner, right? So he will never visit a closed restaurant. And we also want something more. We want all of the restaurant to get equal profit. So we want that in a long run, Bob should visit all the hotels in equal probabilities. So this is the task. And now you can see that actually this is in a Hollow-Frankelheimer scenario. Sorry, because there is the information that is coming on the Alice's side that okay, today this restaurant is closed. And after this one bit communication, Bob has to decide that which hotel he wants to visit. If he visit a closed hotel, their payoff will be zero. And in a long run, they should also visit these hotels in equal probabilities. So now this is a restaurant game. So we'll use this notation. This HN 1 by N means if there are N number of hotels and Bob is visiting all hotels with equal probability, like after a long run, the probability will be 1 by N for N hotels. Or someone can make it a more strict version and generalized it that okay, he can visit first hotel with gamma 1 probability, second visit with gamma 2 probability like gamma N. So this is the generalized version on the right hand side. So now we'll focus on this case that they have only one secret channel shared between them. So what are the type of strategies they can use? So the first strategy is called classical deterministic strategy. What is this strategy? Let us try to understand this one. That Alice will do is that he will make a partition of the hotels. Like okay, one is the even partition and another is the odd partition. If the hotel which is closed belong to the even partition, I'll send 0. If the hotel which belong to the odd partition, I'll send 1. Oh, there is a typo actually. In both cases, I'll send it is 0. One is 0 and another is 1. So he is actually informing Bob, okay, one of the hotels from the even number is closed. You should visit a, then the Bob's strategy will be that he will visit a odd number hotel. So in this way, you will never visit a closed hotel. They are making sure of this. Now let's just try to discuss the second strategy. This is called the classical mix strategy. What is the mix strategy? Now Alice is not doing is this deterministically. Alice is actually tossing a coin. Once he received the information that okay, today the ith hotel is closed, he has, let's say there are 10 hotels. So Alice has 10 coin. If the owner says that okay, today the second hotel is closed, Alice will pick the second coin and toss it. If the outcome is 0, he will send 0. If the outcome is 1, he will send 1. So this is the randomness Alice is actually putting by making this coin tossing. Then upon receiving 0, Bob has a n outcome coin. If received 0, then he will choose the R coin. If received 1, he will choose the Q coin. Now he will toss the coin, and depending on the outcome of the coin, if the R1 outcome click, he will visit the first hotel. If the R2 outcome click, he will visit the second close. So this is called the classically mixed strategy. Here you have more mixedness because you are allowing local randomness on Alice's side as well as you are allowing local randomness on Bob's side. Now we'll come to the classically correlated strategy. What is this classically correlated strategy? In this strategy, they have actually a shared coin. You can think of this that someone else is actually tossing a coin and conveying this to both Alice and Bob. Or you can think of this like they have in the past they have met and they have tossed a coin and they have noted down the outcome and this is correlated. And depending on that, they will choose their strategy. So now they can correlate their encoding and decoding strategy. Like now Alice can choose the kth classically mixed strategy, and at that moment Bob can also choose the kth classically mixed strategy. So now their strategies are also correlated. So it is trivial that actually in this Hollow-Frankel scenario, the ordering between these strategies are actually classically deterministic strategy is the smaller set. Whatever you can do by classically deterministic strategy, you can do that by classically mixed strategy. And whatever you can do by classically mixed strategy, you can do by classically correlated strategy. So the classically correlated is the stronger set. But we want to see whether there is a strict subset inequality or not. So actually in our case, we are actually showing that if you consider, just a minute, my skin is fully visible, right? Hello.
Yeah, I can see your screen full.
Okay. Actually, there is some problem on my side. That's why. Okay. So now we are actually considering let's consider a special case. Like we are considering the 3 restaurant game. Let's say there are 3 restaurants, and we want Bob to visit them in a long run with gamma 1, gamma 2, and gamma 3 probability. Okay. Now, what are the possible scenarios that they can do? Actually, we have shown that okay, this plot, if you see that these plots actually show that this below axis is actually gamma 1 equal to 0, correspond to 0 probabilities, and this point is actually correspond to gamma 1 equal to 1, and all the other values gamma 2 and gamma 3 are 0. Now all the regions that are in the pink shaded, they are actually unphysical because all the hotels are closed with 1/3 probability, right? So the visiting probability of any hotel cannot be greater than 2/3, otherwise you will be visiting a closed hotel sometimes. So only these pink regions are all the unphysical games. You cannot own those games. Now we have shown that if you used convex mixing of these classically mixed strategies, then with the classically deterministic strategy, all you can achieve is these boundary points, these black boundary points. So what this point actually means? This point actually means this that gamma 2 equal to 0, gamma 1 equal to 2 by 3, and gamma 3 equal to 1 by 3. So actually you are visiting if all of these points are actually 2 by 3, 1 by 3, and 0. And there are 6 points with this mixture. So with the classically deterministic strategy, what you can do is that at max you can get 2 by 3, 1 by 3, and 0. Now if you apply classically mixed strategy, you can do the you can use local randomness and have some application on individual Alice or individual Bob side. So they can achieve this individual all these points with the classically mixed strategy. With the classically deterministic strategy, they can achieve only these extreme points, these points. With the classically mixed strategy, they can achieve all these in between lines. So only the border lines are possible with the help of classically mixed strategy. So if you don't have any shared randomness, only with the help of one qubit communication, only these tasks are possible. So all this region within this green shaded region is not possible by one qubit communication only. But let's say you have a shared randomness shared between Alice and Bob. Then what is the status? Can you do something? So once you have a shared randomness, you can achieve any of these in between points because now you can correlate your strategies. So let's say you have a classically mixed strategy for this point, and also Alice and Bob has a classically mixed strategy for this point. Now what they will do is that they will share a coin that with p probability give you head, and with 1 minus p probability will give you tail. Then with this classically shared randomness, they can correlate their strategy with p probability with these things and 1 minus p probability with these things. So they can achieve this red point. So with the help of shared randomness, any point within this region is actually possible. And the game that we have started with at the beginning is this red middle region that, okay, they will be visiting all the restaurants with equal probability. So if you want to achieve any game which is within this green region, you require shared randomness. So this is actually showing that shared randomness is giving you advantage on top of 1 qubit communication. So it is actually increasing the utility of this classical this classical channel. Now, what you are using is actually a classical system. But instead of that, we could have used a quantum system. What is, if you want to do the same task by sending a quantum system, what is the status there? So focus on a prepare and measure scenario. So depending on the information, let's say today the ith hotel is closed, the referee will give that information to Alice. Then Alice will prepare a qubit system from the blocks pair. Like let's say it could be a mixed state. Alice will prepare a row I and send that qubit to the channel to Bob. Now, after receiving this quantum system, Bob will perform a n outcome measurement. And whatever outcome will click, if the mth outcome click, Bob will decide, okay, I'll visit the mth hotel. This is the most general quantum strategy in the prepare and measure they can consider. Now let us try to understand what is the status of this game in this scenario. So this is the same graph that I have already discussed, right? This line corresponds to gamma 3 equal to 0, and these points are like individual 1, 0, 0 probabilities. This is the simplex for the 3 hotel. And here also we are actually focusing on the 3 hotel case only. So what they are actually doing is that, let's say these are the 3 preparation. If the first if the information is given that okay, today the first hotel is click, so the Alice will prepare this psi1 state. And if the second hotel is closed, Alice will prepare the psi2 and psi3 state. This is the 3 state on the great circle of a block sphere. Now, upon sending these things, Bob will perform this measurement. These measurements are completely opposite to the preparation. So if the state psi1 is being prepared, pi1 will never click. The probability of clicking pi1 is 0. So this will make sure that okay, Bob will never visit a closed hotel. But we want to make sure that in a long run, they visited all the hotels with equal probability. So for that, what we have to do is that we just have to adjust this angle of this triangle. So there is 3 points, right? So this middle point actually correspond to this value that okay, we want to fix this gamma 1, right? Now if you keep on changing this preparation, this middle point m23 will keep on shifting. If you fix this psi1 and then you keep on changing this psi3 such that this middle point is actually shifting, so this will give you this like one of the probability will be fixed, like gamma 1 is fixed, but now we can vary this gamma 2 and gamma 3. Now doing this angle, we can change to it any angle, and whatever correlation that you want to generate within this green region can be achieved by this quantum prepare and measure scenario. Just accordingly, suitably, you have to choose the locus of this middle point. Like this blue locus correspond to some gamma 1 value, then the variation of in gamma 2 and gamma 3. Then this blue line is again some other fixed gamma 1 value. So in this way, you can achieve any of this correlation. So if you are sending a quantum system, you don't require any shared randomness. Without the help of shared randomness, you can do these things. Okay. So let us try to understand what is the advantage of this thing. So actually, in this scenario, we have shown that if let's say instead of this, Alice is doing the encoding in on a orthogonal system, like only let's say 0 and 1, or let's say in the plus and minus basis, only in the orthogonal basis, then there is no advantage. So actually, if there is no, if we are not using the superposition, then we will not get the advantage here. Only using the orthogonal state will not give you any help. As well as on the Bob side, if Bob does not use any non-projective measurement, then there will not be also any advantage. Like Bob has to do some non-projective measurement, then only the advantage will be there. So the power is actually coming from the superposition of the qubit and also on the non-projective measurement on the receiver end. Okay. So for the summary of the result that I'm talking about is that we'll use some notation. Let's say A equal to B. This implies that they provide the same utility in all tasks in Holloway-Frank scenario. Means these two resources A and B are same. A is less equal to B, that imply that okay, B is as good as A for any task. Whatever A can do, B will do. But there will exist some task where B is actually better than A. And if we use this symbol that A is less equal to instant B, that implies that okay, there exists a task where B is better than A. But we cannot comment whether for every task B will be as good as A. So once these notations are clear, so then let us try to understand this first line. This is actually the superdense coding protocol that I have already discussed. That if there is a maximally entangled state assisting a quantum channel, then the capacity of this is actually greater than quantum. Now there is a famous paper by Holloway and Frankel-Weiner. Pardon me, this paper is recently published in Quantum. So they are actually showing that okay, if you have a maximally entangled state, the communication utility of a classical channel can be enhanced with the help of this one maximally entangled. So qubit plus one qubit is actually powerful than qubit. They have another result in their CMP paper that I have already discussed, that okay, if you consider shared randomness as a free resource, classical communication is as good as quantum communication. So now considering our game, we have actually showing that okay, the analog of this superdense coding result, first line, that the shared randomness can enhance the power of this classical communication and it can do some task way more better than this classical communication. And also we have shown that that I'm discussing this quantum protocol, that quantum can give you advantage over the classical. This is not new. We already know that quantum can give you advantage, but in Holloway-Frankel scenario, this is a new result. We know that in RAC kind of scenario, quantum prepare and measure actually give you more advantage. And these things are actually I have not discussed in our talk. These are in details in our paper. We are actually considering some GPT system. Those are actually post-quantum theoretical models of nature. And we're actually showing that okay, if you send a event gone system, GPT system, that is actually more powerful than classical system. And there are some other results also where we are actually showing that this amount of shared randomness is actually powerful. There exists some task, if you have log 3 amount of shared randomness, you can do it, but with one shared randomness you cannot do. So shared randomness amount as you keep on increasing, the number of tasks which you can do will keep on increasing. So the amount of shared randomness is also playing a crucial role here. Okay, so these are the details things you can look into our paper. I'll not go into the details. So for the conclusion, I would like to say that okay, our work being forward the efficacy of classical shared randomness. It is giving you the flavor that how classical shared randomness can help you to empower the utility of classical communication. And I must say that it had been already studied that how classical shared randomness can give you some non-trivial advantage, but that is in the asymptotic limit, that if you have asymptotically many copy of classical channel and the shared randomness is asymptotically free, then what is the advantage then that you can reveal from there? But we are actually considering a very different scenario. We are considering only finite number of set, like single shot. We are using only one single shot classical channel, and how the utility of that channel can be enhanced with the help of classical shared randomness that we are studying. And it will be exciting to explore this trade-off between this amount of shared randomness and the amount of classical communication required to perform a task. There is a trade-off. As you keep on increasing the amount of shared randomness, you can do more tasks. So before ending my talk, I would like to thank all of my collaborators, Mirda, Somrat, Sahil, Edwin, Tamal, and Somda. And we are all doing this a collaborative talk, work under the supervision of Dr. Manik Purik in Esenbos National Center. So thank you, everyone.
Thanks, Ramakrishna, for this nice interactive talk. So now our session is open for quick question. Participants, you can ask question or write the question in chat box.
Thank you for your talk. One clarification question.
Yes.
Could you please explain what is non-projective measurement. In your, I think, talk, I heard about non-projective measurement. So what is this?
Oh, non-projective measurement means that you have to do this POVM measurement. You are not doing this orthogonal projective measurement like this. You are, let's say, you are performing a measurement in, let's say, let's say that 0 and 1 basis. Like in the Z orthogonal basis, you are performing a measurement. So this is actually
Okay, so this
projection
is
on the subspace.
Okay, so this is POVM.
This is the actually projective measurement. Actually, you are projecting the system on a subspace of 0 and 1. But instead of that, in the measurement, actually we require that, okay, this should be the positive elements and they should adapt to identity. So they need not be projected, like p squared need not be equivalent to p. So you can see that in case of quantum, the measurement that I'm taking, they actually adapt to identity, but they are not actually this p squared is not equivalent to p. So they are actually not projecting the system to a subspace.
Yes. Thank you.
Are there any other questions from audience?